Going on to another tool the mathematicians have in Section 3 of Unit 4, permutations and combinations. We'll look at permutations, combinations, and guidelines on which method to use. And we'll start off first with what is the definition of a permutation. So, in the context of counting problems, arrangements are often called permutations. The number of permutations of n things taken r at a time is denoted by this formula. And this is what you want to have in your notes. This is the permutation formula. And it's somewhat related to the fundamental counting principle and a little bit to factorials as well. Here we see the relationship of permutations to its factorial representation. So in this slide, what we'd like to do is work some of these out. It's 1 pp. In the arithmetic form in which we use this, we're keeping in mind also that in your calculator you will have a key for permutation, and putting this in to check it would be a useful tool to know how it works. Alright, so we have here our n, which is 5 factorial, divided by 5 minus 3 factorial, which will be, as we see here, 5 times 4 times 3 times 2 factorial. I'm stopping there. Divided by, now we do what's in the parentheses first. 5 minus 3 will give us 2 factorial for our denominator. And then using that technique that we spoke of in the last section, these cancel out. So we go 5 times 4 is 20 times 3 is 60. So that works out nicely. Now, for letter B, this is going to be 6 factorial divided by 6 minus 6 factorial. So we have 6 times 5 times 4 times 3 times 2 times 1. Now 6 minus 6 is 0 factorial, and we had said that 0 factorial was 1, so all of this is over 1, and 6 factorial, which is this, comes out to 720. Now again, this can be put into your calculator, or it can be worked out mathematically using this formula. We want you to have skill on both sides of this. All right, let's take a look and see what we have here. And there it is. All right, example 2. How many ways can you select 2 letters followed by 3 digits for an ID if repeats are not allowed? Well, this is a permutation problem, so we'll set it up as P, And for our, let's keep in mind what we're doing here. We're having 2 letters followed by 3 digits. So how many letters do we have in the alphabet? Well, there would be 26. And how many are we selecting? These 2. So that would be 2. And this would then be times how many symbols do we have for digits? This is another permutation. And there would be 10 of those. And how many are we selecting? 3. So something like this, rather than work it through arithmetic, we would just put that into our calculator, and you would go 26, select P, 2, times, then 10, select permutation, 3, equals, and this comes out to 468,000. Wow. And again, this is a method of fundamental counting principle where we're using this special tool, permutations. And there we see it. Now you want to be sure you have some good notes. These will make up our quiz questions. All right, example 3. Building numbers from a set of digits. Now, how many 4-digit numbers can be written using the numbers from this set? Well, there are 1, 2, 3, 4, 5, if repetitions are not allowed. Well, this would be a permutation. We have 5 for our n value, and we're looking for 4. So again, we put that into our system, and since this is a small one, we can work it out mathematically. This will be 5 factorial, and this will be, in parentheses, 5 minus 4 factorial. Now, 5 factorial times 4 times 3 times 2 times 1, because when we do our subtraction here, we end up with 1 factorial, which is 1. So it's going to be 20 times 6 here, which will give us 120. So again, some of these are easy. This previous one was a little challenging, but you want to know how to put this in your calculator and how to apply the formula and then do our substitution to do our calculation. And there is the work. Another method is what we call combinations. And in this case, the formula for combinations, we use the letter C. It's set up similarly, but here the order over here, let me underline this for you. The order of elements makes no difference, while in permutation, order was significant. Combinations, order is not significant. And as we look at the formula, it's similar, but we have a few changes. just note this in your notes, that here we are, in a sense, dividing by r factorial, which gives us our permutation is divided by r factorial, because those would be things that were repeated. We talked about lookalikes before, so that's brought in. Now, thankfully, you don't have to memorize all of these formulas. Your basic choice will be, which do I use? Permutation or combination? And then often we're going to just put this in our calculator. So let's do one here. We'll do the first one mathematically. So I set this up, 5 factorial divided by our r, 3 factorial, and then 5 minus 3 factorial. So this will be 5 times 4 times 3 factorial. You'll see why I'm leaving it like that in a moment. And then this will be, I'm going to put this 3 factorial here. Just switching that around. And then what will this be? 5 minus 3 is 2. So this will be 2 factorial. Here I can just cancel out these. So this is 5 times 4 is 20. And 2 factorial is 2 times 1, which is 2. 20 divided by 2 gives me 10. And let's set this one up too. So as we continue this, our n is 6, our r is 6. So 6 minus 6 is 0 factorial, which is 1. So actually here we end up with 6 factorial divided by 6 factorial, and anything divided by itself is 1. All right, let's check this out here. And there we see it. Again, that was example 4. Be sure you're labeling your work. All right, finding the number of subsets. Now, if you recall, subsets, the order is not significant. So we want to find the number of different subsets of the size 3 in this set, where there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So since order's not important, it's combinations of 9 items taken 3 at a time. So our n is 9 on top. 9 factorial. Our r is 3 factorial. And then it's going to be 9 minus 3 factorial. So this is going to be 9 times 8 times 7 times 6 times 5 times 4 times 3 factorial for sure. And this 3 factorial is this one that I put here that I can later cancel out. But when I do this, I get 6 factorial. 9 minus 3 is 6, so this is 6 factorial. So I'm going to change my mind. I'm going to do 3 factorial here after all, and you'll see why in just a moment. Okay, so notice that if I eliminate all of this here, this is 6 factorial. That's the better way to do it. So I'm going to cancel these out. Now 3 factorial is 3, 2, 1, which is 6, which is 3 times 2. Hopefully you're all following all of this. This is gone now. So 3 times 2 times 1. Now I can take a 3 out of there once. 3 out of there is 3 times. 2 out of there is once. 2 out of there is 4 times. So now I get 12 times 7 here. 12 times 7 is 84. So again, try it, put this in your calculator, should get 84. But we also did it arithmetically. Let's check it out. And there it is. And they're not showing us how we're doing some division here. All right, example 6 now from our PowerPoint slides. A common form of poker involves hands, which are called sets, of 5. Now, so in setting this up as a combination, because the order of the hand is not important, we have 52 cards in a deck, and we want to select 5. So it ends up 52 factorial divided by 5 factorial, which is our R value, and then 52 minus 5 is 47 factorial. And we don't want to have to write out all of this. Putting this into your calculator, in fact, from this position, gives you 2,598,960 different possible hands from a deck of cards that has 52. Wow. Now, this chart I have on the second page of your booklet for this section is like super important. So we're going to take some time to go over it with you. Here are your permutations, combinations. They both rely on selecting R items out of N items. This is your total. This is the grouping that you want. And for both of them, repetitions are not allowed. Now, which one did we say order is important? Permutations. Which one order is not important? Combinations. And again, their arrangement of items, these are the formulas. Again, the N factorial should be on top here. I don't like the way they did that, but that's okay. Now, there are some clue words. What's a clue? Well, you have to decide which one are you going to use, permutations or combinations. Some clue words, arrangement. So if something is arranged in a special way, that's a permutation. Some sort of schedule. Again, a schedule is arranged in a particular way. Order implies a particular way. These are permutations. Clue word for combinations would be just a group. So, for instance, if you had a president, vice president, secretary, treasurer that you were going to elect in this order, that would be a permutation. But here, if you were at a club and you were just going to elect committee members, here's a committee member, here's a committee member, here's a committee member, it doesn't make any difference. Order would not be important there. that would be a combination. If you have a sample of something, is order important? No. Selecting something, selection, order not important. So again, you have this to look at, and then with study, you'll be able to hopefully apply the correct value for permutation or combination as you do your formulas. And again, you'll be using your calculator for much of this. Okay, we're now ready to go into our textbook. Now, all of these examples are in your lecture booklet. So, again, you may show some arithmetic work, and also useful in the skill of practicing how your calculator works to get answers. So these are just to evaluate. So pause, see what you get, and then I'll give you the answers. Now they're working them out arithmetically as well, but these are the answers. So I would suggest you illustrate using these formulas and knowing what they mean, and then of course have your answers. You'll be doing this in homework, and then you'll have a few of these on your Unit 4 test. All right, a few more examples again, calculating them, in this case, from your calculator. Pause and check it out. Noticing letter C here, they're illustrating this in scientific notation. All right, here we have to decide whether we're going to use permutation or a combination. How many non-repeating 3-digit numbers? Now, is order important in numbers? For instance, if we had 1, 2, 3, and then we had 3, 2, 1, are these the same numbers? No, these are not the same numbers. So therefore, order is important. So here we would use permutation. And we have 1, 2, 3, 4, 5, 6. 6 is our n value. And we want to select 3. So put that in your calculator and see what you get. And there it is. And there's our answer. Now, for example 4, take a moment to read it. So we have 2 letters followed by 4 digits. And then 3 more letters, where repetition of letters are not allowed. So is order significant here? Yes. So we're going to use permutation. So we have 2 letters out of how many? N would be 26. Now for our second group, we're using digits where we have 10 symbols. We want to select 4. And then we're using our letters again, where we want to select 3. And again, putting this into your calculator, 26 p function 2 times 10 p function 4 times 26 p function 3 equals and it would be 51,105,600,000. So you see the process. And some of these are challenging, and hopefully, you're getting to use your calculator properly. Okay, we're jumping in now to combinations where order is not important. They're showing us the formula again, and you're just going to pause. And again, you need to write these in your booklet over on the right there. And there's the arithmetic of it, the calculation, and the results. Are you getting these when you put them into your calculator? And again, evaluating using your calculator. Be sure to include the answers in your booklet, and you know how to do this, the strategy, the protocol. Now here's a hint that our textbook gives us, and we've mentioned this. First of all, you're using permutation and combinations when repetitions are not allowed. And for the combination, order is not important, while in permutation, order is important. Okay. Now here we're looking for subsets. Now for subsets, did we say order was important? No. So this is going to be a combination problem. And to save a little time, we'll just go directly to what the book is offering. There are 4 for our n value, 4 symbols. We're going to select 2 at a time. There's the calculation, and it ends up as 6. And they're also showing what the subsets would look like in their combination. In example 8, we did this one already in the PowerPoint slides. When we are dealing poker hands, set of 5 cards, this would be a combination because order is not important. There are 52 cards in the deck. We want to select 5. How many do we have? Well, if you recall, this was a quite an extraordinary large number. 2,598,960 possible different hands. So, I don't know if you ever play solitaire online. I enjoy that. And you keep asking for different hands, and they're just one little card different from the whole previous section, and it's a new game. All right, let's go on. For number 9, Carrie wants to buy 10 different paintings, but can only afford 4. How many different ways can she make her selection? Again, order is not important here. And so it would be 10 is our n number. Combinations, because order is not important, would be 4. Again, putting this into your calculator, you could physically work it out, but there are 210 ways. This is what you want. Now, they're showing us here that she's supposedly not selecting 6 paintings. And that comes out the same. That's sort of interesting, but we don't want to complicate this. But while we're on this page, for those not acquainted with cards very much, there are 4 suits of cards in a deck of 52. Now, one suit is called spades, and it's black. Another is called clubs, and that's black. So spades and clubs are black. Then there are diamonds, is another suit, and hearts, another suit. They're red. Now we're going to use this a lot in other sections in Unit 4 when we do probability, because as you can imagine, playing cards and gambling involves the science of probability, which is related to what we're studying in this unit. Now, as we look through a deck of cards, we have an ace, and then a 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the regular cards. And then we have face cards. Face cards would be the jack, the queen, and the king. And we find this array in each of the suits. And there's 13 cards in each suit. So there are 3 of these cards that are face cards. So in a deck, there would be 12 face cards. Okay. Well, a little background, and we'll review this when needed as we go to future lessons. But I thought since we had the picture there, we would use that. Now we've gone over this chart. This was rather important, and I don't think we need to review it. I have it included in your booklet. And here is a summary of problem-solving hints. Now remember, we've had 3 counting methods already. We had fundamental counting principle. We have now permutations and also combinations. Now there is a relationship of factorials to all of these, and sometimes one could be used in the other, but you often want to pick the easiest method depending upon characteristics of the example they're asking you. And of course this will be featured on the test. So look at these examples, spend a little time reading them, and noting the method they're using to solve it. In example 10, in how many ways can a mother distribute 3 different toys among her 7 children if a child may receive anywhere from none to all 3 toys? Reflect on that for a moment. And because a given child can be a repeat recipient, repetitions are allowed here. So for this, we would use the fundamental counting principle, and it would be 7 times 7 times 7 ways those 3 toys can be distributed, which gives us 343. How many ways can a 3-member committee could appoint Club N appoint so that exactly one woman is on the committee? Well, again, this is from a previous section where we're going to see our 5 committee members. Alan and Bill are male, David is male, Kathy and Evelyn are females. So notice that you want to select one woman is on the committee, so this would be a combination of combinations. So for the first one, you would have 2 women in a combination. You're going to select one. That gives you 2 ways. And then you have 3 men. You're going to then select 2 of those 3 men. That gives you 3 ways. So 2 times 3 is 6. So there are our committee members listed. This was the type of vid that they did in that section we skipped back in 4.1, where they were actually having us go through the listing of things. Here we're using mathematical techniques and computation to figure these out. All right, here we have Alpha Beta Gamma fraternity would like to attend a special event this weekend, but only 10 members will be allowed to attend. How many ways could the lucky 10 be selected? Now, is order important here? No. So can you see N is going to be 48, and we're selecting 10, and this is a combination, as you see here. And again, over 6 billion ways. Wow. Numbers get quite extraordinary, and if we were trying to list them. Okay. Now, here, when we have 10 fraternity men, they arrive at the event. 4 of them are selected to escort 4 homecoming queen candidates. And how many ways can this selection be made? Well, now, here, one of the fraternity fellows will be paired up with a particular homecoming candidate. So this, in this case, order is important. So we have 10. Permutation, we're going to select 4. So 5,040 possible selections. Again, you'll be doing your homework and having to make these decisions and hopefully improving your skill as you go along. Now here we're going to divide a group of baseball lineup players here, 9 members, a group of 4, a group of 3, a group of 2. Now, is order important here? Well, this might be tricky if you're thinking in terms of batting order, but they're just saying selection. So order would not be important here. So you would set it up 9 for our first N, and you're selecting 4. Then, since you no longer have 9 to select, it's 5. You're going to select 3. And then later, you're going to have 2 left and selecting 2. So here it is set up below. If you get one like this in your homework, then this is a model that you can follow. And you end up with 1,260. Now, this one's a little tricky. And as you'll see, you may not get the right answer on the first shot, because here you want to take those same players and divide them into groups of 3. Now, you may think it would be like this, and you would get this, but here, order of the 3 groups is not important either. They're indistinguishable, because all group sizes are 3. So they suggest you're then going to divide this by 3 factorial, and then in this case, there's only 280. Now on our quiz and on our, generally the homework, and especially on the test, we're not going to pick really challenging ones. You're going to be dealing with the more basic patterns of what we're illustrating here. This one could be a real challenge. And I believe this is our last slide, and yes, it winds up what we're doing in this lesson.